I was going to say this morning, but it's morning here and afternoon there. So I guess I'll say this afternoon or morning. We're going to talk about calibration, embedding, and de-embedding, and how it is that we can get highly accurate results, particularly with the Bode 100 and Bode 500. So this is going to cover an awful lot of ground, but we're going to talk about why it is that measurements do have errors, what those errors are, what the differences are between calibration, embedding, and de-embedding, and how it is that we use those. What's the difference between measuring at 50 megahertz and 450 megahertz in terms of calibration complexity and cost? And what are the results? After all, nothing's perfect, even calibration. So what are the remaining errors? And how do we deal with things like test fixtures and additional adapters and cable extensions and things like that? So hopefully we'll cover all of those topics today, and at the end, you'll be experts in how to get really accurate measurements. But before we can talk about making accurate measurements, we have to kind of define what that means. What are we trying to measure? And so if we were to look at typical measurements today, especially in power electronics, we could look at the kinds of things that we often measure. We might be measuring inductors or capacitors. Those are probably two really frequently addressed components. And in the case of a VRM output inductor, switching regulator output inductor, we might want to measure the DC resistance, and that can be on the order of, I've seen them as low as about 125 microohms these days. And if we wanted to see the self-resonant frequency of a typical VRM inductor, that's typically going to be in the region of about maybe 1 to 2 picofarads. And if we wanted to accurately measure a capacitor, in particular the ESL of a typical 0603 capacitor today is about 200 picohenries. And so let's just say that for the sake of argument, we wanted to be able to measure these three terms, the DCR, the parasitic capacitance, and the ESL. And if we looked at those magnitudes and said, all right, we would like to achieve 10% accuracy in our measurement. That's arbitrary, but 10% is probably about the lowest accuracy we would find ourselves comfortable with. Well, that would say that we need to be able to measure capacitors to an accuracy of about 100 femtofarads. We would need to be able to measure inductance to an accuracy of 20 picohenries, and we would want to be able to measure resistance to about 12.5 microohms. And that would get us 10% accuracy. And so that kind of just puts a point in the sand for what it is that we think we need to be able to measure. But the truth is that it's not stopping, and it's getting harder all the time. In here, I made a few measurements just to kind of show where it is that we're at and where it is that we're going. In the green trace, I just measured a 1.2 nanohenry chip inductor, and it was really just for the purposes of getting something on the screen that we knew the answer to, and to show that we got that right. And you can see in the cursor table that it says that our 1.2 nanohenry inductor is 1.17 nanohenry, so very close. And then we measured a few different components. We measured a 50 milliohm resistor. That's a current sense resistor. It's actually a resistor that Picotest will be making shortly, and it's down in the range of about 50 picohenries. We have other 50 milliohm resistors that are even lower than that for high bandwidth measurement at 25 picohenries. And here we can also see in the blue trace a 3-terminal capacitor, and that's measuring about 165 picohenries. So while we're saying that we need to be able to measure to an accuracy of maybe 12 picohenries, well, at this one all the way on the right, our 50 milliohm 3-terminal cap, that would be a 50% error. So we really need to be able to measure much more accurately than even that. And the question is, how do we get there? Well, first, we have to measure something we know before we can measure something that we don't, and it needs to be close to the same magnitude. Sometimes that's easier said than done. But what we're going to do before we even start calibrating, we're going to make a few measurements of known devices without calibration, just to show what the errors are that we're supposedly going to be correcting. And so in this case, we're measuring 125 micro-ohm resistor. It's actually one of the Picotest ULVR sample resistors. It's a resistor standard made for the purposes of validating measurements. That's something that we know. And if we measure this in an uncalibrated measurement, you can see in the top window we have the magnitude, and in the bottom window we have the phase. And I identified places that are incorrect, that they're errors. And so in magnitude on the left-hand side, you can see the ground loop error. And so even though we have 125 micro-ohm resistor, we're measuring somewhere closer to 12 milliohms, or roughly a 12,000 or 10,000% error due to the ground loop. You can see by the time we get to about between 10 and 100 kilohertz, the measurement is correct. And then at 100 kilohertz, we can see that it becomes inductive. And that's all well and good until we get to about 300 megahertz, and then we can see that there's a resonance there. Well, one of the interesting things about this measurement is that if we use the cursors and look at the inductance, we can see that the inductance at 10 megahertz says that it's 163 picohenries. And if we take the magnitude at 10 megahertz and divide it by omega, we get 164 picohenries. And those two are in really good agreement. And they're in really good agreement because we can see that sloping line for the inductance. We know it's inductive because it's increasing impedance at 6 dB per octave with respect to frequency. And we can also see it in the phase that at 10 megahertz, we happen to be at just about 90 degrees. But we can also see in the phase chart that the phase moves around an awful lot. And it also moves a decade before and a decade after poles that show up in the magnitude. And it turns out that that's an important thing. So starting with this 10,000% calibration error, I wanted to point out that we really can't correct that with measurement. I mean, I know the numbers work, but it doesn't really work. I got this analogy from a paper I was mentoring. I think it was 2 years ago, not this past DesignCon, but the one before that. And I really like this analogy, so I stole it. And it says that we can't really create calibration corrections for large errors like that because it's the story of the elephant and the feather. And the story of the elephant and the feather says, I want to know what the weight of a feather is. And there is a way to very accurately do it using an elephant. And so we take an elephant and we weigh him holding the feather, and then we weigh the elephant without the feather. And if we take the difference in those two numbers, we'll accurately know the weight of the feather. And it's sort of the same thing when we talk about trying to create a correction for this 10,000% ground loop error. The numbers work. And yeah, we could measure 11.6 milliohms, with the cable error, and we could subtract 10.475 milliohms from the measurement to get the correct 125 microns. But there are a lot of other things to consider that would also show up as errors. And so it wouldn't be an accurate measurement. And those include things like cable deformation and pressure sensitivity, contact resistance in probe pins, almost everything that could have even a very minute change in the resistance would show up as an additive error. And so in the end, we can't really correct this error directly by subtraction. And so what that means is that before we can try to correct it with calibration, we need to improve it to the maximum extent possible. And we do that in the two-port shunt-through measurement by adding a ground loop isolator, either a ground loop isolating transformer or a solid-state isolator. But we do something in order to try to minimize the impact of the ground loop error before we try to correct it. And these errors can be minimized. In this example here, I'm using a setup that we created actually for Isvan Novak at Samtec. I wanted to be able to measure 1 micron accurately. And in order to do that, we need to do a few things. One is we have to remove the ground loop error, and measuring down at single-digit microns requires enormous common mode rejection on the order of about 100 dB. And so that's what we did. We made a flat response 100 dB ground loop isolator, which is the right half of our J2116. We also added a high gain source power amplifier on the left side to boost the signals up to get better to signal to noise ratio. And so long as we can keep those responses very flat and frequency independent, and we can keep the connections matched to 50 ohms, we can theoretically get a very good measurement. And so here we made the measurements of a lot of our resistor standards, and you can see down in the bottom legend what the actual value of the component that we measured is. We also included the noise floor, and we measured a short, a perforated short for comparison. And you can see that we do have an impedance floor here that's below a micron, and we were able to measure magnitudes of 2.2 microns reasonably accurately using no calibration at all, but flat gain components that provide the ground loop isolation to correct the low frequency error and gain to improve the signal to noise. And so this is a pretty good measurement, even without calibration. We do need to add the ground loop isolator, but which ground loop isolator do we need to add? And this depends on a number of factors. One is how low is the impedance that you're trying to measure at low frequency? How big is the ground loop error? And how high in frequency do we need to measure? So here I'm just showing a few different isolators. In the purple trace, I'm showing 125 micron measurement using our J2113 solid state isolator. And you can see that that does correct the ground loop all the way down to 1 hertz. And in fact, it goes all the way down to DC. And it's pretty good to above 100 megahertz, just above 100 megahertz, again, without calibration. If we look at other calibrators, well, we can look at the J2102B in the blue trace, and you can see that that's pretty decent. It gets a decent 125 micro measurement by the time we hit 1 kilohertz. So it's not great below a kilohertz, but it's pretty good above that. You can also see once we get above 100 kilohertz that they all converge on the same inductance. So they all agree at that point. And you can see that in the blue trace, the transformer provides less wiggles above 100 megahertz than the purple trace does. So it's a pretty good measurement, even well above 100 megahertz. And the resistor without any ground loop correction at all, you can see we do have this very large 10,000% error at low frequency. And again, it corrects itself, but at a higher frequency, maybe around 10, 20 kilohertz, it gets okay. So the choice in how we isolate the ground loop and which ground loop isolator we need is dependent on how much attenuation we need of the common mode error and also how high in frequency we need to measure. Honestly, for most people, the J2102B is a very good choice. It's kind of in the middle. It won't go down to DC, but it does have pretty good high frequency response and pretty good common mode rejection in the middle. And it's also one of the less expensive isolators. If we want to make measurements of devices, we want to measure much lower than that. So in this case, I chose a chip inductor, a 603 chip inductor. And I chose one that was 1.2 nanohenries. And I did that because that was the most precise I could get. It was 1.2 nanohenries plus minus 100 picohenries, which is an 8% accuracy on the inductance. We could get 1 nanohenry chip inductors, but those are also 100 picohenries, so that would be 10%. So by going to the 1.2 nanohenries, we actually get a better tolerance. We could get even lower inductances and maybe even better accuracy in a smaller size, like a 201, but it becomes really difficult to hand solder those. And I wanted to keep this pretty simple, so I mounted an 0603 chip. That's 1.2 nanohenries. And again, I measured this without any calibration to see where the errors are and what it is that we need to correct. And here on the left, you can see I drew a green box around the ground loop error. So there is still a significant ground loop error. Not quite as big as before because the DC resistance is much higher, but still about a 26% ground loop error. But now if we look at the inductance, you can see we calculated the inductance from 2 magnitudes of cursors, one at 10 megahertz, one at 100 megahertz. And you can see we end up at 10 megahertz with 1.38 nanohenries. At 100 megahertz, we end up with 1.26 nanohenries. The part is specified at 100 megahertz. So that's actually pretty close. We're measuring 1.26 nanohenries for a 1.2 nanohenry inductor. That seems really close. But then if we look at the cursors, you can see the cursor tells us that at 100 megahertz, it's only 600 picohenries, which would be 100% error, or 50% error from the magnitude of the measurement. And so what's the deal here? And how is it that we can get the right answer by calculating it from the magnitude and not the right answer when we use the cursors? The reason is because the phase is really important. And here we can look at the magnitude of the error, and we can also look at the phase error. And you can see that the phase changes a lot, but it also changes a decade before and a decade after the magnitude changes. And so at low frequency, you can see in the bottom window the error that we have at 3.8 hertz. And you can see that big phase dip that occurs as the ground loop isolator is starting to get corrected. By the time we get to 380 hertz, we're within 1 degree of the right answer again. But then when we get to 100 kilohertz, you can see that the phase is already increasing significantly 100 kilohertz, while it didn't in the magnitude. And so the problem is phase correction. Now we look at the same thing with a capacitor. We can do the same thing. Here's the measurement of a capacitor. And we measured it without calibration, just like before. This is a 4.7 microfarad cap. On the left-hand side at low frequency, you can see that the measurement kind of craps out and we don't get the right magnitude below 10 hertz. And that's because we're very close to a S21 of 1.0. So we have very poor sensitivity at really high resistance. And in fact, 10,000 ohms is probably well above what would be recommended for a two-port shunt-through measurement. But and we can see the resonance and we can see the ESL on the other side. And then we can see some imperfections in the fixture that I highlighted on the right-hand side. And here we can look at what these magnitudes look like. So we took 2 points on the inductive side of the capacitor. We took the impedance magnitude divided by omega, and we get 581 picohenries at 10 megahertz, 500 picohenries at 100 megahertz. And yet when we look at the cursor table, those don't quite agree. But you'll see at 10 megahertz, it's actually really close, 576 picohenries versus 581. And then when we measure it at 100 megahertz, you can see that we calculate 500 picohenries from the magnitude, 277 picohenries from the cursors. Again, we end up with a very significant error. And that's because these are uncalibrated measurements. But now we have pretty good insight into what it is that we're attempting to correct for. And we've also learned that the goal is to minimize the errors before we try to correct them. So first we have to define a couple of terms. What is embedding? Embedding is the addition of elements such as fixtures or amplifiers to the measurement. And I showed that with our J2116. We didn't add calibration, but we added an amplifier that had gain, and we added a receiver that had gain, and we corrected those just by adding or subtracting the gain terms from our measurement. And you can do that in a math trace, or you can even do that with the probe factors in the Bode 100 or Bode 500. De-embedding means that we're going to subtract something from our measurement, and that's usually that we're subtracting things like a printed circuit board or an adapter or a cable. And so we want to remove those. We remove those from the measurement by de-embedding. Calibration is a little bit different. It's not a post-process. It's a pre-process, and that is that we measure something that we know, and we tell the analyzer what it is that it's supposed to measure, and the VNA measures all of those points, and it calculates correction factors so that when it's finished, it measures what it is that you told it was supposed to measure. And that's done generally by the use of a cal kit. The cal kit is software, and it can be in the form of coefficients, like I'm showing here on the right lower right corner. It can be a file. But it's software that the VNA uses that's associated with the calibrator. And it says, if you're going to use this calibrator and you want to do an open, you should be measuring this. And if you measure a short, you should be measuring this. And to measure a through, you should be measuring this. And it tells it what all of the correct answers are. And then the VNA is adjusted to make all of those correct measurements. The way that it works in a traditional VNA, and I'm using the Copper Mountain S5085 as a traditional measurement, it's a traditional vector network analyzer. We go into the calibration menu, and you can see it tells us all the calibrations that we need to do. We have to do short, open, load on each port, and we have to do either a through or a reciprocal measurement to get the through path. And of course, we needed to tell it what it was that the right answer was. And the way that we do that is by selecting the appropriate cal kit. The calibrator that I showed in the previous picture was an S911T. That's a 3.5 millimeter 9 gigahertz calibrator. So we choose that one, and that tells the vector network analyzer what the right answers are because it has the cal kit stored for that calibrator. And we do use a torque wrench, and it's really important, especially when we make higher frequency measurements, that we use a torque wrench. And we'll talk a little bit more about why soon, but that does ensure that we get the highest accuracy when we made our connectors. We can do even better than that. There are automatic calibration modules that are available from most vector network analyzers from those companies. They're a little bit different in that it doesn't use polynomial coefficients to do the calibration. It actually has stored data, and it's a little bit more accurate. It's data-based, it's temperature compensated, and so the automatic calibration module is more accurate, but also that means more expensive, and most of them are actually traceable to the National Metrology Institutes. And a lot of these automatic calibration modules also include measurements that it shows up in memory of the vector network analyzer. So it shows your measurement and their measurement just to make sure they agree, and that's supposed to give us higher confidence in the measurement. But now, what is really important about this, and where do these errors come from? And after we do the calibration, what kind of things change? So here I created a very simple simulation model. It's a two-port model to represent our two-port shunt-through measurement. And I just added two perfect time delays, one on each side of our dot. And you can see that I put a dot in the middle, which is a capacitor, which I represented here as an RLC. I could have made a much more accurate capacitor model, but I wanted this really simple one because it tells us exactly what the right answer is. So we know this is supposed to measure 300 picohenries because we put it there. And now I took this total time delay of the board, which is kind of fixed by the size of the board, and I just moved where it is that the capacitor is using this term K. So one side we're calling K, and the other side we're calling 1 minus K, and that allows us to move the component back and forth along the board, while we can use the time delay to change the actual time that it takes to get through the board. And here we can see what that error looks like. Even in a very tiny printed circuit board that has an ideal path with no losses, you can see that we end up with very significant errors, particularly at the higher frequencies. And that's because of the fact that, number one, we have this delay that needs to be accounted for. And number two, the traditional VNAs and receiver-based Z-domain VNAs measure differently. And so S21 is often the path that's used to calculate the two-port shunt-through impedance. And many of us know that impedance is 25 times S21 over 1 minus S21. And that is a very simplified approximation. But it also assumes that our path is 50 ohms. And if we add a delay, well, that starts to look inductive. And so at higher frequencies, it's not 50 ohms anymore. And so a 25 S21 over 1 minus S21 and a true two-port shunt-through measurement start to diverge by around a couple hundred megahertz. After all of this, our measurements are still wrong. And how come? The reason is that electrons actually move relatively slowly. I mean, they move at roughly the speed of light, which sounds pretty quick, but electrically, that's not so quick. It's moving at about 300 millimeters per nanosecond. And delays shift the phase, but they don't really have an impact on magnitude. If we want to measure to an accuracy of 0.2 nanohenries or 0.2 nanohenries per millimeter, it means that we need to get our distance measurements, the electrical length, accurate to within about the thickness of a Post-it note. And that's one of the reasons that we use our torque wrenches to try to make sure that we make a very accurate engagement distance in the connector center pin, because if that were to change just a tenth of a millimeter, it would have a very significant difference in phase angle. It really is that sensitive. And here what I did is I reduced the delay times in our very simple simulation just to see how it is that those errors change with time delay. And you can see that as we reduce that time delay, our 25 S21 over 1 minus S21 and our true full two-port measurement converge perfectly. And now you can see the phases and magnitudes are perfect overlays. And so what controls the delay? A couple of things. One is the dielectric constant of the printed circuit board that we're measuring on. Small RF material printed circuit boards have smaller phase error than FO4. They're also a lot more expensive, but they also have better control on the tolerance of decay. And so this is really what we're sensitive to in this measurement, is the electrical distance between the two connectors. Even if we were to make a perfect mount, and then we did this measurement after calibrating the instrument, and we make a simple through measurement, you can see the phase is still wrong. And how can that be? We just went through the process of calibrating the instrument perfectly using a high quality calibrator, and yet it's still wrong. And the reason is that when we calibrated to the ends of the connectors on our cables. And now we added a printed circuit board to mount our component, and the printed circuit board itself adds yet another delay. And that delay is represented as phase. And so now we would need to de-embed the printed circuit board in order to get the correct answer. How do we do that? In a traditional vector network analyzer, there's two ways to do it. If the path is perfectly 50 ohms, we can use port extensions to just tell the instrument how long that printed circuit board length is electrically. Most vector network analyzers can also do that automatically, and it will measure the printed circuit board itself and accurately remove it. If the printed circuit board or fixture isn't a perfect 50 ohms, then we go to something called automatic fixture removal. And what that does is makes a measurement. It figures out what the fixture looks like on the left side of the component, what it looks like on the right side of the component, and it creates de-embed files that it embeds inside the instrument to remove those errors in order to remove the fixture. Another way we could do this is we could actually make half-board calibration. So what if we just took our circuit board and we cut it in half, and actually physically did that here, so you can see the full board on the left and the half board on the right, and now we could actually do open, short, and load on a half a circuit board, and then we could measure through with the full circuit board, and theoretically that would also get us the correct answer. So what happens if we take our same 1.2 nanohenry inductor, we do the calibration, and we add the port extensions in order to remove the effect of the printed circuit board, and now we're getting much closer. You can see we still have a low frequency error because we didn't correct the ground loop error. You can see the phase now is very close to 90 degrees, and you can see that our mounted chip is measuring about 1.45 nanohenries. All we've done is calibrated the instrument to the connector ends and tried to de-embed the printed circuit board using port extensions. And we can do the same thing with our capacitor. And here now you can see we have 3.56 microfarads. Again, you can see we have a low frequency error, but we're close to 90 degrees. At the higher frequency on the inductive side, you can see again we're close to 90 degrees. And now you can see that we're measuring 334 picohenries, which is very close to the right answer, and 90 degrees. So what's next? Next, we measure each component without calibration and using two-port shunt-through calibration, and we measure with calibration using short and iso-short standards. So if we take the 1.2 nanohenry measurement with and without calibration to compare them, now we can see where the errors lie, and I've circled them here for you. But you can see in the lower left, we still have this ground loop low frequency error. At the high frequency, you can see the inductance looks about right. There's some wiggles compared to the post-calibration result, but we're actually pretty close. And yet when we look at the phase, we can see we have a huge phase error, and we can even see the standing waves as the pattern repeats through the phase errors. And that occurs starting at, well, just a few megahertz. And so the magnitude is really close, the phase isn't, and pre and post calibration is pretty close in magnitude. And if we do it with the capacitor, you can see it's very similar. Low frequency, the traces are overlaid almost perfectly. High frequency, we end up with a couple of wiggles due to the fixtures. And yet when we look at the phase is incorrect at both low frequency and also at high frequency. And again, we can see standing wave reflections. What if we try to measure this 1.5 picofarads? We said that we also need to be able to measure 1.5 picofarads to see self-resonant frequency. We said that's really high impedance, well above the range that's typically recommended for two-port shunt-through measurement, but we're trying it. We got a 1.5 picofarad capacitor, and we do the calibration to measure that, and we get 1.6 picofarads. Down here at low frequency, you can see we're getting 0 degrees, and then here at higher frequencies, we're getting 90 degrees, and yet when we look at the traditional VNA, it's sitting there at 0 degrees. The resolution of phase, again, is in our way. What this means is that the phase accuracy of the VNA has some limitations, and the limitations are going to appear in a couple of places. One of them is going to be the Q. So when we want to measure Q of an inductor, that takes the real and imaginary terms, and we end up in a measurement that's very, very sensitive to phase angle. And so typically we can't measure high Qs using vector network analyzers, but the better we can get that phase measurement, the more accurate it will be. We need to get the phase right in order to get the Q right. And if we want to use cursors to measure things like inductance and capacitance, that's using imaginary terms. It's also very important that we get the accuracy of the phase correct. The typical VNA, traditional VNAs, are typically accurate to about 0.5 to 2 degrees, but that's a pre-calibration accuracy. We can improve that if we know the accuracy of the calibrator itself, and then the accuracy is defined by the calibrator. And so all of this is really only important to us because we cared about how we could make accurate measurements in Bode 100 and Bode 500. And we needed to have something that we could compare it to that was highly accurate. And the only highly accurate measurements that we have are traditional vector network analyzers that use NIST traceable calibration. So we're using the traditional VNA to provide the NIST correct answer. And now we can use the Bode 500 to figure out whether or not we get the right answer. There are differences between the way that Bode 500 calibrates versus traditional VNAs. One is that the Bode 500 doesn't offer calibration kit support, so we can't tell the Bode 500 what the right answer is. It doesn't use short open load through or short open load reciprocal for two-port measurements, and it doesn't offer port extensions, fixture removal, or embedding and de-embedding. But on the other hand, it offers Z-domain calibration, which is very different than a traditional analyzer, and that's a much more direct calibration, which makes life a lot simpler for us. The lack of CalKit support requires that we have to calibrate a little bit differently, and that's what we're going to talk about next. So for us to do the modified short open load calibration in a Bode 500, we perform an open using a printed circuit board without a component installed. And so a two-port through is the same thing as an impedance domain open. And so you can see in this calibrator, we have the traditional open short load standards. And then there are 3 specifically for the Bode 500 through, which is a two-port Z-domain open, ISO short, which is a perfect short with the correct electrical length between the two sides, and a Bode load, which is a two-port shunt 50 ohm load. And so we perform the open short load in Z domain, and if we can manage to get those standards to be nearly perfect, we'll get those all correct. But the next question is, how short is short? Well, I tried using a piece of wire, and you can see that one in red, and that ended up being about 340 picohenries. The interesting thing about that is when we measure the capacitor, you can see now the capacitor has a negative inductance, and that's because the inductance of the capacitor is less than the inductance of our fine gauge wire. If we go with a low impedance short, well, we end up with still the ground loop error. That's the iso short part. So we need the short because if we don't have the short, we don't get the correct ground loop error. But we also need as much isolation as we can get. This particular isolator is showing 400 femtohenries as residual inductance. The one I showed you in the picture is currently below 100 femtohenries. Now, this could lead to what we call accidental de-embedding. And like I said, when we put our shorting wire, the shorting wire had a higher inductance than a component of the physical size. And so if we do the calibration using the wire and then measure the component, well, we end up with a negative inductance because we've overcompensated for the inductance, we've removed too much, and we accidentally de-embedded the electrical length of the component. And so we have to be really careful not to accidentally de-embed, and we'll talk about that as well. If we put all this together now, and we look at our pre and post calibration measurements, we can take a look at the measurements that we got from magnitude only, and we can look at the measurements that we get from the cursors, and you can see that these two measurements agree really well. So 341 picohenries versus 341 picohenries, 1.4 nanohenries versus 1.4 nanohenries, and 11.5 picohenries versus 11.5 picohenries. So if we can do the calibration right, we will get the cursors and the impedance-based magnitude measurements to agree with each other. And here, even at 1 picofarad, you can see that we have the roughly 3 femtofarad impedance ceiling, and we were able to measure 996 femtofarads for our 1 picofarad. So the takeaway is that it is really possible for us to make extremely accurate measurements, so long as we can get the calibrations to be perfect. So in the final comparison, we take the 1.2 nanohenry chip inductor and we mounted it on a Picotest component mount that matches our calibrator. And now you can see that we made the measurement using two devices, the S5085 using an ACM 2509 NIST traceable automatic calibrator, and port extensions, automatic port extensions for the removal of the printed circuit board. And then we measured the same chip cap on the same board using the Bode 500, calibrated with our 2.92 millimeter calibrator. And here the two measurements are overlaid, and you can see the impedance magnitude in the upper left. We can see the imaginary part in the top right, and you can see the phase in the bottom left. And I even calculated what that inductance error is. You can see the difference between the traditional calibrated VNA, NIST traceable, and the measurement that we made with the Bode 500 using an accurate calibrator. The difference is only 3 picohenries. Somebody's going to ask me which one's right. I don't know. I can tell you they're 3 picohenries apart. They're both really good measurements, and which one is more accurate be really hard to tell. One question I do get a lot is, what about probes? I mean, this is all great, and measuring with connectors is awesome, but when I get to probes, what's the difference in the errors? Well, there's a little bit of a difference. One is that we can't get rid of the coupling between the pins that are very closely spaced. And so the probe is never going to be as good in high frequency measurement, particularly in an integrated probe like the 2-port probe, but we can still accurately calibrate it. It does need an iso short calibrator, which isn't currently in our standard, but we will measure it and we'll add it. Also, probes have an added difficulty that the pin resistance is sensitive to pressure, and so we can have small changes in our measurement just due to the contact pressure of the point. And so why do we use them? We use them because they're just really convenient, and but they won't be as accurate. Component test fixtures are similar. You can see here, our own component test fixture. You can see our impedance ceiling is up around almost a mega ohm, a couple 100,000 ohms. But note that we talked so much about phase accuracy and how important the phase is. Notice that we're not showing that here we're only showing magnitudes. But we showed the measurement of milliohm, we showed the measurement of 10 milliohms, we showed the measurement of capacitors. And so the next thing to assure would be that we measure the phase accurately. And again, same thing. We need highly accurate, ideal calibration standards, including ISO short, open, and load. We talked again about embedding and de-embedding, and this is the way that we embed, and this would work the same way if you wanted to add a BAMP 12. BAMP 12 has 12 dB gain, and so yes, we can calibrate it, and that'll work really well. But if the gain is 12 dB and flat response over frequency, we can also just add 12 dB to the measurement, and we should get the correct answer. A couple of tips that I wanted to provide for really accurate measurement. One is that you really need to use properly designed Kelvin mounts. The Kelvin mount has two requirements. One is that it be accurately 50 ohms, because it does need to look like just a port extension, or it's going to end up with wiggles in the waveform. And it needs to have 4 contact points that are well defined, because if we don't have 4 points, then we'll end up with residual inductance from the interconnect. You need to use short phase stable cables, and ideally with screw tight and properly torqued. I generally prefer to use either the end connectors with SMAs at the other end, or an end connector with an SMA adapter. I typically try to avoid BNC connectors for this particular measurement when we're going to make really accurate measurements. One reason is that phase stable cables are pretty stiff, and we put a wrench on them and turn them, we tend to unscrew the BNC. And so we end up spending a lot of time trying to figure out why it is our measurement doesn't look right, and it's because the BNC got unscrewed. Also, we can't torque a BNC connector, so contact resistance can be variable. So we generally prefer not to use BNC for our highly accurate high-frequency measurements. PDN cables are relatively phase stable, and so they work pretty well for this. Choose an isolator that's based on the required CMR and the frequency range that you want to measure. And really importantly, remove as many errors as you possibly can in the setup and the fixture first. Calibration corrections are generally intended to be minor adjustments, not huge adjustments. Remember that calibration changes the measurement. That means that it can also degrade the measurement. So it's often a good idea to look at the results with and without the calibration turned on, just to make sure that they look similar. Measure something you know first and make sure that it is the same magnitude as the measurement you're trying to make, because that's the only way we can get confidence that our setup is accurate enough for the measurement we're trying to make. Be careful not to unintentionally de-embed any elements, and that means that if we place a wire to short a pair of component pads, it's really important that if we want to de-embed that measurement, that the inductance, the wire that we short the pads with, has exactly the same inductance as the component we're intending to remove. So you can't just solder a wire and expect you'll get the right answer. You won't. It's often better to avoid using the phase data, especially when you're measuring extremes. The phase changes a decade earlier and a decade later than the magnitude changes. And so we can recognize an inductance by the fact that it's increasing at 6 dB per octave with frequency. We know that it's inductive. We may not know that it's perfect 90 degrees, but we do know that it's inductive. The phase is going to be all over the place if it's not corrected, and the higher the frequency, the larger the impact of the phase error. When measuring extremes, try to measure quickly after calibration and do the most important calibration last. And that means that if we're measuring, picohenry ESLs, I always do the short calibration last, and I do it always just before I make my measurement. So even if I'm calibrated, when I'm ready to make the measurement, I'll do another short calibration just before I measure the ESL that I'm trying to measure, and that'll get me the most accurate result. And that's everything that I have to tell you about calibration. And in the end, we were able to measure with an accuracy of better than 3 picohenries. So thanks, and if anybody has any questions, I'm happy to answer them.